much for this very nice opportunity. It's really great to talk after already two talks on the topic by Silvia and Malco. This is really nice. So yeah, fortunately, a lot of the introduction for the topic is already done, and so I'll try to be a bit quicker. And so I'm gonna tell you about these works that I did in collaboration with Apple team and Slava. So there are two outs and some one or two to appear soon. So I want to start by a disclaimer that yeah, there are like 50 years of work on this subject. There are many people worked on this, and so these are just a few of the people that work on this. So I'm not gonna be able to review the work of everybody. I'm just gonna tell you about what we did. And hopefully then in the discussion, we can also see that how everybody else tried to approach the problem. So the motivation, you already heard it, but let me tell you, like in a few minutes, what is my personal motivation is this really beautiful picture that it was clear from the previous talks. So that when you study the IR fixed point of this model with random field, the Ising model, you see that sometimes there is this emergent supersymmetry, and so I call it this Parisi-Sorla SUSY, and also that there is a connection to the pure model that is just the Ising model in lower dimensions. So this is like a really beautiful picture that arises in this topic. And so it's really interesting to study. And however, as we already heard in D equal 3 and 4, this picture fails. Well, it seems to work in 5D, and okay, in D equals 6 and higher, then you get the hypercritical dimension, so it's just a free model. So what is the motivation of this talk is to understand when and why this works, but through some techniques that are really like basic quantum field theory techniques, for example, epsilon expansion. And so, yeah, we had two works, and so our point of view was to divide and conquer. So one division that we did is to try to keep separated the SUSY part and the dimensional reduced model, and try to study the connection separately. So we had the first work on this connection and the second one on this connection. So this talk will be mostly about the second paper, and so about this connection, but I'll start with one quick review about this part. So this, that is just here. So this connection, the reason why I want to be quick on this is that the punchline is that it should just always work. So if you have SUSY, this kind of special supersymmetry introduced by Parisi-Sorla, you will have by default dimensional reduction. So this model, this SUSY Ising model, will be just described by the model in lower dimension. But let me tell you what we actually did. So this work is kind of as a bootstrap spirit. So it starts by defining the conformal field theory, so just by purely axiomatically, if you want, with this extra supersymmetry of this Parisi-Sorla type. And we defined this model. So what did we do? We studied the representation theory. We studied special multiplets that can appear, like the stress tensor multiplet. We studied correlation functions, and everything with this kind of supersymmetry. And this is a first part of this paper. And the second part is to actually check what happens with this dimensional reduction. So how this CFT in lower dimension emerges. So the idea is really simple. It's just that you imagine that you have a correlation function with many points, x1 to xn. They would be in RD, but you plug them in just in this RD minus 2 space. And then this, just because of the features of the supersymmetry, you will get that what you get is something that looks really like a full-fledged conformal field theory in D minus 2 dimension. And there is some magic in this story because there is some decoupling of infinitely many operators. And thanks to this decoupling, we were able to, in practice, match how the operators of the higher dimensional theory would would map to the lower dimensional theory, how you would get also stress tensor, how the OPE works in the lower dimensional theory. And even for this OPE, it's very interesting because we saw that the operator...
Sorry, question. You can do also, for example, for branching polymers?
Yeah, actually, I will comment on that, but yes, we can do also branching polymers. At this point is really just, we didn't even specify what is a theory. It's really purely any theory with this kind of supersymmetry. So it works for anything. And so it's really very abstract. But I'll also comment on this connection about the branching polymers. Yes. And so an extra feature is for this OPE is that there's in practice a one-to-one map between the operators exchanged in the OPE of the higher dimensional theory and the lower dimensional theory. And this is very unusual because you would expect that in lower dimension, you would have infinitely many operators for each operator of the higher dimensional theory. And this gives you also, if you want, a relation between the conformal blocks. And you see that there's, for each conformal block of the higher dimensional theory in D dimension, so this is a super conformal block. This will be just equal to a usual conformal block in D minus 2 dimension. And this relation gives rise to a purely kinematical relation that works in general, that is very cute. That is what I draw here in this box. And in practice, it's just equivalent to this formula here. And it's due to the fact that each super block can be expanded in a finite sum of usual blocks. And so this tells you that if you are given any conformal block in D minus 2 dimension, this is equal to a finite sum of blocks in higher dimensions. And this is just a purely kinematical statement. So it's just works for any theory. But we found it just studying these properties of supersymmetry. So it's quite a cute result. But I mean, beside this this story, I mean, the punchline is that we don't find anything weird in these theories, and that there is something that looks really like dimensional reduction for these theories, and so we don't find anything wrong here, and so we just think that this connection should always work. And so, for example, in this talk, I'm going to use this connection as something established. So the question is instead this connection, and so the rest of the talk will be about this. So the question is there, here I'm gonna do this arrow here is a big arrow, is this arrow, and you see it's gonna be complicated to get to the final part. And so I will keep this map to remind you where we are. And the idea is that we want to see when this random field theory will actually have in the IR will have emergent supersymmetry, and where it will not. The argument is, in practice, an argument that we borrowed by Calvi in 84, but we added a few steps, in particular these red circles, if you want, are what we introduced. And so I'll try to tell you what we did. So what Calvi did was, in practice, going here and then jump here. But let me tell you about this story. So we will start by the random field theory and do the replica trick that now you are all expert about. And from the replica trick, we will use this argument by Cardi that will just be using some map in field space, and we will rewrite the replica fields into some new basis that will be this Cardi basis in using this Cardi transform. And this Cardi transform, we will I mean, the new thing is that we will get a new way to approach this theory through the RG. Well, let's say that Calvi had some argument that was not using RG, was just saying, well, doing a few, I mean, with some approximations that were not really under control, he was able to get to the SUSY part. But what we argue is that actually you don't need to add some approximation. You can just do RG and you get something that we call, let's say, a leader theory that describes the IR. And from this theory, we will see that sometimes you get SUSY and sometimes you don't get SUSY, depending on what I'll tell you later. So this is the picture, and I'll try to go through this map. So the first step of this map, you know it very well, is the replica trick. And so let me just start by the definition. You already know this very well. We start by the random field theory already in the continuum. So this is the action. So you see here I have introduced a coupling H that has a Gaussian distribution. So here I have a capital H that is the variance. And okay, I'm writing a potential V that could be in principle generic, but for the Ising model it's just phi to the fourth. So we are considering lambda phi to the fourth. And so the problem of this theory is that it's not quite a quantum field theory. And so let's say that to do RG with this theory, it's a bit trickier. So what you would want to do is to have a normal quantum field theory without any field that is it's random. And so you do the replica trick, and you get this replica theory that is the one written below. So now you have n replicas that are coupled through this H that is this parameter. And then you want to take the n going to zero limit. And this is supposed to describe the same random field theory. I also have a slide that I will go through in like 10 seconds, since you are all experts on this. How to see this is that when you take the average of this, the random average of correlation function in the random field theory, as you already well know, you will have this 1 over z that is a complicated beast, and then you want to average over the disorder with this Gaussian distribution, this part, but this 1 over z is complicated to deal with. So you multiply and divide by z to the n minus 1, then you put together the denominator and you get the z to the n, and in the limit n going to 0, this is just 1. And so you just get rid of this. And instead you put together these n-1 replicas to inside this exponent, and you get n replicas here. And the cool thing is that now you can just switch the integral, the path integral in the phi and the integral in h. You can perform it, and you just get this action here that is the one that I wrote in the previous slide. So in practice, what you get is that this kind of observable can equally be computed as a limit of n going to 0 of a correlation function written in this way, where the action is just this one here. But okay, you all know this very well. And so let me just tell you about what is a Cardi transform and why we would want to do something else beside using the replica trick. So the problem is, if you want, it was already there in the previous two talks when in the replica formulation, you see that this correlation function, the propagator between two replicas has two different powers. And indeed, this was related to the connected and disconnected correlation function. But yeah, so this also means that the field phi itself doesn't have a nice scaling behavior because it has two pieces. So the RG in these variables phi I is a bit complicated. So what we would want to have is a theory where each field has a nice scaling in K. And so this is achieved through Cardi transform. So Cardi transform is simple. It's just this map here. So instead of having the field phi i's, we map them to this Cardi phi, omega, and chi. You see that there are like chi i's, there are n-1 of them with one constraint. And so on this side, I defined rho is just the average from phi 2 to phi n. And by just this linear map, so there's no assumption in when we do this, we get that the action, the Lagrangian becomes this one. And okay, let me just make a disclaimer here in this talk, since we saw it in the replica trick, we found that you work at n equal to 0. In this talk, I'm not gonna bother keeping n. I'm just setting n to 0 in all formula. And there's in the paper we had more reasoning to do that. But here, I mean, it's quite I think it's quite natural. We had a limit n going to 0, so we set everywhere n to 0. So the result is that we get this Lagrangian, and this Lagrangian has a very nice scaling. So in particular, if you write the propagators are like exactly what we wanted. Each one had a precise scaling in K. So in particular, you can assign to this field some nice scaling dimension. And by the way, you can see from here that phi is below unitarity bound. So it's d over 2 minus 2. And so you already know from here that the theory that you're going to get is non-unitary. And okay, so here we are already at the Cardi transform. Do you have any question about it? Or if not, I'll go to the part that is the new part, which is this what I call here this IR leader theory. So this is just coming out from like trying to do RG with discarded variables. So let's say that now we have this nice theory, we believe it is the correct one, and we have scaling dimensions for each field. And so we want to do RG. What do? As usual, we just classify all possible singlets with respect to the symmetries of our theory. And then we see what are the perturbations that are relevant, irrelevant, and we study the model. And so the first step is then to classify the singlets. So, and what is the symmetry of our theory is Sn for the replicas. So we can permute all the replicas. So this is Sn symmetry. And plus we have Z2 symmetry because we are considering the Ising model that has this phi to the fourth potential. So you have an extra Z2 symmetry. And to do RG is actually simpler to, I mean, to classify the singlets is actually simpler to do it in this phi I variable, so using actually a replica variables, because the Cardis ones, as you saw before, are not, I mean, are not manifestly Sn symmetric. You are choosing here some special direction. And so it's a bit harder to find directly the Sn singlet in those variables. So what we do is to find them first in terms of the phi i's. And we write here, for example, these are examples of this. You have this sigma case that is just phi I to the k. And of course, this is an Sn singlet, but then you can dress it with some derivatives, and we call it in this way, or you can dress it in different way with derivatives. And then you can take linear combinations of these, and this is the kind of Sn singlet that you can have in your theory. Then the second step is to actually map them to Cardi bases. And this is, I'll give you some examples. So what you would want to do is to start by the lowest dimensional operators. And so, for example, all the quadratic operators, I write them here. And you would recognize that, so these operators correspond to build up this Lagrangian that was the one that gave the free propagators. So this is the free part. Then you would get some sigma 2, and this is like a mass term. So this is a strongly relevant interaction that you would want to tune when you do RG. And so this is the strongly relevant parameter to tune. And then you would want to go on. The fact is that this is a bit tricky because when you go on, the next operator that you would find is already a quartic operator in the phi fields, and when you map it to Cardi bases, you see that is actually a very complicated beast, a sum of many terms, but the complication and the feature that is very, very weird is that actually these different terms have different dimension with respect to the free dimension that I wrote before. So you would want to compute everything using this dimension. So even in free theory, you would sum those dimensions here and find that these are different. And so we call the lowest dimensional one the leader, and then all the other ones will be, this has a bit higher dimension, this is higher by some integers, and we call them followers, follower 1, 2, 3, and 4. So this looks like a very weird feature of the theory, but remember, I mean, we started by fields phi I that didn't have a scaling, didn't have like a nice scaling. So when you actually write these singlets, you do not expect in some sense to get nice scaling. And this is what we indeed find. And in general, if for a generic operator O, you will always have leaders and followers. Indeed, the weird, the counter example is the quadratic operators. So these one do not have followers. These actually have nice scaling dimensions. So this is probably the reason why this model was not studied so much is because this looks very daunting. So how do you treat this? Since you have that the singlet is a sum over operators with different dimensions. But so we tried to actually go on, and we have a recipe, and that is motivated by RG. So the recipe is that actually the followers can just be killed in the IR. So in the IR, they do not quite matter. So when we want to study the IR properties of the model, in practice, the leader will be the only thing that we want to study. Let me just try to...
Emilio,
sure.
The leaders are supersymmetric and the followers are not supersymmetric. Right?
No, no, I'm not saying that so far. Actually, there are leaders that are also non-supersymmetric. I'm gonna tell you about that.
Because
later.
you start from some singlet which is not taken into account by...
As you will see later,
okay.
yeah, there's
okay, I will see later. Thank you.
That, actually, I mean, you in principle can take also linear combination of this. I mean, now this singlet sigma 4 is written this way, but you can also take sigma 4 minus, I don't know, sigma 2 squared or something like this. And you will see that in some cases, actually, the leader will not be supersymmetric. And okay, also you are getting a bit ahead because so far I'm not talking about supersymmetry at all. So yeah, bear with me. Anyway, so the idea is so far I just want to motivate why the followers do not matter. And this is actually true all the time. The reason is because when you do RG, you do an RG step. The RG step is made out of two pieces. One is integrating out degrees of freedom. The other one is to rescale back your cutoff. So here, for example, I'm considering a cutoff lambda prime equal to lambda over some parameter b that is bigger than 1. And we are integrating out this shell. And by integrating out, you will see that, I mean, since you had this ascent symmetry, this form of the ascent singlet will be preserved. So you can only change the overall coupling. So if you put a perturbation of this kind in your Lagrangian, you will see that after integrating out, you change only the overall coupling. But now you want to rescale back to the previous cutoff. And when you do that, you see that, okay, beside the rescaling the coupling, you also rescale each followers with different powers of B, which depend on how much it was the dimension of the follower, I mean, the different dimension of the follower with respect to the leader. And you see that in the IR, when you take B large, in the deep IR, these terms just drop out. And so in practice, when you take the beta functions for this coupling, this is just, it's the same as the beta function for the leader. And in practice, so this tells you that if the leader is a relevant, so if it has a relevant dimension, then this is it's a relevant perturbation, the full SN perturbation. Well, if it's irrelevant, the full perturbation. So let's say that the full SN singlet is just governed by the leader. This is the statement. And so let me summarize this statement. What is the leader theory? It's a theory where we keep only the leaders, where you take all your operators that are singlets, and you just keep the leaders. And how to find these leaders is very easy. You just write them in these replica variables where it's easy to write. You do the Cardi transform, and then you drop the followers. That's the recipe. So this leader theory...
I have a question. this is true also, like if in the renormalization procedure, I mean, like let's say, feeds with some followers produce another family of. I mean, it cannot occur that two fields, one field will get normalized, on another field.
Yeah, you will see that. I mean, you can indeed you can generate other fields. I mean, it's not fully diagonal. The RG, of course, you have mixing, but it's interesting because you see that the leaders mix just. I mean, mix in a non-trivial way just among themselves. And so in practice, there is some extra symmetry, if you want, that is probably due to this sense symmetry that is giving you this extra structure. So in practice, you are actually safe to study the leaders.
Okay. Yeah. Thanks.
So the interesting result is that now we have a theory that we can build up, and this theory is what we can start with and do RG with that. And so now I'm gonna tell you how to get the SUSY part. So I'm gonna go to this direction, and this is
just another question, maybe very naive. So as long as you go with the down in dimension, say from dimension 6, the dimension, the scaling dimension of the fields changes. I mean, yeah. Can't you have a sort of collision of dimensions of leaders and followers?
No, actually, so the followers, I mean, I didn't tell you very well this point, but the followers actually have exactly do not renormalize with respect to the leader. So the difference of dimension of the follower and the leader stays the same along the RG. Okay. So yeah, and it's always some integer difference. So it's, and okay, so let me tell you how to get to this SUSY theory. And the idea is that, I mean, you get to SUSY when you just study d equal to 6 minus epsilon for small epsilon. And in that case, you are safe and you can get to the SUSY fixed point. And how to see it is just that, okay, now you start by your leader theory. And so you just classify all the possible leaders that you have in these dimensions, which are relevant. So which are those? So you see that again, as I wrote before, you get this free part of the Lagrangian, plus you have this strongly relevant interaction that you want to tune to 0. And then you want the leader for sigma 4 that is this term. And this is weakly relevant. So you see the dimension is 6 minus 2 epsilon. And so this actually, so the reason why we start by this dimension is because there is one single weakly relevant interaction. So you can do perturbative RG. You have this short RG flow. You can just do usual epsilon expansion. Notice that you can study all possible leaders, but for epsilon infinitesimal at this point, they are all irrelevant. So you just can drop them. And so in this situation, you get that your Lagrangian is just this one. And you go on, you have your Lagrangian, and you can compute all observables, and you will see that this Lagrangian actually give you the same critical exponent as the SUSY Lagrangian. And you may ask why, and this actually it's already explained by Calvin 84. The reason why is just, it's very simple. It's just that the sky field have some emergent O2 symmetry. So in particular, the chi is just quadratic, enters the Lagrangian quadratically, and so since it's quadratic, it's in practice Gaussian, the path integral in terms of these chi fields. So you can perform it, and you find some determinant if you want, and so you can just exchange the usual ideas that when you have a Gaussian bosonic path integral, you have 1 over the determinant, while when you have a fermionic one, you have a determinant. And so you see that here you have -2 fields, so you would have this determinant to this power, but it's equal to do a similar Gaussian integral with some Grassmann numbers. This would give you this result that for n going to 0 is the same. So in practice, you can, every time you have terms of this form, you can just map them in this way, where this psi and psi bar are just Grassmann numbers. So they are not spinors. Another way to say this is that this has O-2 symmetry, and it's known that O-n is theories with O-n and theories with SPN compute the same observables. So in practice, when you do this map right here, you get a Lagrangian that is this one. And this Lagrangian is actually the SUSY Lagrangian that was written by Parisi and Soelas. And so this is the reason why after all this idea in 6 minus epsilon, you write this one, and this one can just be mapped to this one, and it's in practice SUSY. And as you already saw it in the previous talk, there's also a superspace formulation where you just introduce superfields of phi, which package all these phi, psi, psi bar, and omega in terms of an expansion in some fermionic degrees of freedom theta and theta bar. And you have also the super Laplacian as you saw before. And so this is, it would be the SUSY. And just to tell you, let's go back to one of the first slides of this talk. Remember, for this SUSY theory that would be here, this link always work. But what does it mean for us? It means that, for example, if you take the 2-point function of this curly phi, this can be computed in terms of a 2-point function of this psi, phi hat, which is just a field of a 2-dimensional pure phi to the 4 model. So this is just usual Wilson-Fisher. And so this is it's a great thing because I mean, a lot of observables are just very well known in Wilson-Fisher, and so we will use this to compute things of the SUSY theory, to compute any observable of the SUSY theory. But okay, now I told you how to get to this SUSY theory. Let me now tell you when this SUSY fixed point is not reached. And the idea is that, okay, we were working in 6 minus epsilon, and I told you that when epsilon is infinitesimal, indeed, I told you which are all the possible relevant perturbations, and the model then, after exchanging free boson to free fermion, would give rise to SUSY. But what about if epsilon is of order 1? At this point, maybe you can have other relevant perturbations, and this relevant perturbation could spoil this supersymmetry. So this is the logic, and the cool thing about this leader theory is that now it's very easy also to study all possible perturbation. And actually, we can even find some extra symmetry and let's say classify them according to some extra symmetry. So let me tell you about the possible types of leaders that you can have. So this will also answer the previous question. So the SUSY types of leaders are actually what we call the SUSY writable, and they are of this kind of form. So they are like of the form chi squared. So this is the important part. So there's an ON-2 symmetry for the chi fields, and times, okay, any function of f or omega. Well, actually, any times you have ON-2 symmetry, you would get this SUSY writable. And the reason why they are SUSY writable is just that you can map these chi's to psi's in this way. And so this is just a SUSY operator. Then you can have some operators that we call SUSY null. These are interesting. They are a bit subtle. They are of the kind chi squared squared. And you see that when you apply this map from chi to psi, you get that this object is mapped to psi bar squared. But since you're squaring fermions, you're just getting 0. So this object would be cannot be actually described in the SUSY theory because it's just 0 there, but it exists as a leader. Then there are other operators that instead, they don't have this extra ON-2 symmetry for the chi fields. You have just Sn-2. And these are all fields where you have like a chi to some power higher than 2. So this is the classification that we have for the leaders. And what we did then is to just classify all of them for like up to very high dimension. We studied up to dimension 12 at d equal to 6. And we wrote them down, all of them, and we classified them in each type. And then we studied if they were becoming relevant or not. So we studied anomalous dimensions at 1 or 2 loops, and we studied if they were like becoming relevant, and so spoiling supersymmetry or not. There's an extra simplification that is very cute, is that of course all these SUSY writable operators can be actually mapped to this SUSY model, and so they, as you know, the SUSY model is captured by Wilson-Fisher, and so you can just use the results of Wilson-Fisher. But in Wilson-Fisher, you know that all operators are irrelevant, okay, beside this phi hat squared, the mass term that you need to tune. And this mass term would indeed correspond to the mass term that I would tell you, I was writing before, this sigma 2 operator. And so it's very cute because we already have all these operators that are already computed in the literature. Indeed, we did check that we get the same result as the Wilson-Fisher. And so it's just a very nice check that everything works well. But beside these leaders, there are extra ones that are non-SUSY writable, and there are actually much fewer of them, non-SUSY writable or SUSY null that you encounter. And the most interesting ones are actually were already considered by Feldman in a paper in 2002, and they take this cute form when you write them in terms of replicas, and you see that these are just phi I minus phi j to some power k, and k of course cannot be odd because otherwise, yeah, by parity this would just give you 0, so it has to be even. And also it has to be bigger than 2, otherwise this is also 0. So the first ones are like the 4 and the 6, and these are the lowest dimensional ones. And so we consider those ones. Well, we consider all these operators, but we notice that those ones are the most interesting ones. And indeed, this F4, when you write the leader, you see that it's the first SUSY null operator. Indeed, it's really this chi-squared operator. And the F6, it has this form when you write it in terms, when you consider its leader. And this is non-SUSY writable. We computed the anomalous dimension of two loops, and then we can just check if they become relevant or not at some dimension. And so here is the plot of what's happening. So here is dimension. So in practice, what we ask is, yeah, we just plot this, considering that d is equal to 6 minus epsilon, and we plot here this line is the marginality line, and so when if this operator cross the marginality line, it means that they become relevant, and we see that the F4 is this yellow line crosses here, and this green line also crosses here, and they both cross between 4 and 5. And so this give us a picture of what we think is happening, and this is the pictures that we have our Gaussian fixed point that would be here. So notice here is the dimension d of the space-time. Here is it's like a theory space, so you would think about all the couplings in theory space. And we see that this is the Gaussian fixed point, and you see that in d equal to 6, the theory is just free, but a bit lower, you start to have a short flow, and you see that in 5 dimension, and the IR fixed point here, this line would be the Parisi-Solas Ising model, so this SUSY Ising model, and what we see is that the flow would reach this SUSY line until a critical point that is between 4 and 5 dimension. Okay, we estimated it in this way. If you want, there's some PADE 1.1 that we use to estimate the error, and we see that here some operators, probably the F4 or the F6, will become relevant and trigger a new, and destabilize the RG and give you a new fixed point that would be SUSY breaking. And so we think that in 4 dimension and in 3 dimension, you would get to this other line of fixed point that starts at some d critical between 4 and 5. And yes, that's it. I mean, this is I leave you with the summary. So this is the idea. What we did, we had these 2 parts, and in one part, it was more about just the dimensional reduction of theories with supersymmetry. And we explained that it was just working nicely. And in the second part, we defined how to do RG with these Cardi variables, and we understood that there is something that I like to call leader theory, and we classified the theories. We saw that there is this nice symmetry, and we classified all possible perturbations, and we found that there are 2, in particular these 2, that are quite interesting because they cross marginality between 4 and 5 dimensions. And so our picture is that between 4 and 5 dimensions, there's SUSY is broken, but it's still, it should be there in 5D. Of course, I mean, I want to say this is just from a 2-loop computation of these anomalous dimensions. So it would be very nice to have higher loops. We shouldn't trust too much the value of the critical. We should, however, I think the most interesting part is that we have now an algorithm to actually compute these dimensions, and it would be nice to go to a higher epsilon. And okay, I think I can end it here. Thanks.
Okay, thank you, Emilio. So, are there any questions?
Yes.
Please go ahead.
Can you show again the picture of your phase diagram with the new fixed point?
Yeah.
Yes. Does the yellow line also continue to the right, although that fixed point maybe becomes unstable in that region?
Well, yeah, you say that, so that there are like
maybe
those
it
operators.
continues like that, and maybe in 5 dimensions you still have the competing two fixed points, the supersymmetric one and the non-supersymmetric one, except that the non-supersymmetric one in that regime is unstable.
Okay, so this I'm not quite sure. So the thing is that well, I mean, this operator that is triggering this RG is, I mean, you can define it in any dimension, but here it will be in higher D, it will be irrelevant.
Yes.
So yeah, in some sense maybe, but I mean, I want to say that we don't know anything about this this line. We just know that there is an extra operator that becomes relevant.
That indeed is my next question. Can you rewrite that operator in terms of the original replica Hamiltonian with the original random field?
Yeah, actually, you can try to do that. There's also, I mean, I was a bit schematic here. There is still a question of how many relevant perturbations do you actually get? Because I mean, as I show, there are two operators that already are getting relevant between 4 and 5, and maybe there are even more. And so yes, you can try to play the game of rewriting them in terms of the original theory. However, I'm not sure if you can quite try to tune them, since you don't know how many you have, and also if you have to tune 2 extra parameters, this could be a bit too hard. So it depends on how many new relevant parameters you have. But yes, you can rewrite them in terms of the original.
Because you see, in the original Aharoni Imri Ma paper, we did not use replicas at all. We just switched on the random fields and then expanded the partition function in the random fields and then averaged, and then every diagram contained the random fields. The random fields dressed the internal legs in the diagrams, and it was straightforward to show that that implies a dimensionality shift. So I cannot imagine how within that framework new operators would be born that might break the continuous line of dimensionality shift results. So if one could rephrase these non-supersymmetric operators back to the original problem with the random fields without replicas, then we might gain some insight on where they might come from.
So what we found, at least, I mean, we tried it in a toy model, if you want, by asking that just this F4 operator would become relevant. And then we tried to rewrite only this guy in terms of the random field. And so in the random field, you can get this kind of perturbation by choosing a different distribution for the random field.
How strange must that distribution be?
Well, that I don't quite remember, but it's just.
That would be very interesting if you could show that there is no universality of distributions, and there are some distributions that break supersymmetry.
It should be a renormalized field distribution, no? That you're looking like in functional renormalization group. Now I had also a question which I think is rather similar to the goes on the same line at least as the one of Amon. Actually, I mean you find that there are operators that break the supersymmetry that become relevant. Now, the presence of these operators, I've shown that. One of the things that I was showing is that one of the word identities of supersymmetry is basically expresses fluctuation dissipation theorem. The fact that when you perturb the system and you are in a minimum, you move along the direction of the minimum in the parabola. So how this breaking of supersymmetry modifies the word identities of the theory? So what did you look at that, or you think it is possible to look at that? It is easy to look at that.
But so you want to see how this perturbation would break supersymmetry? So.
No, I would like to see what additional contribution it gives to the response function, for example.
I mean, I have to say that then the question would be, for example, that, okay, we are considering a perturbation and we see that becomes relevant at some point, but then, for example, if you want to consider what happens in, I don't know, in 4D or 3D, I mean,
if you just, for example, move a little bit below DC or...
Yeah, the question is that even at DC, I mean, it's not quite easy to work out these questions because you don't have access to this to the theory in this line. You just know that something will break, but I mean, this is an RG context. So I mean, when something becomes relevant, then I mean, just the theory is going to be different in the IR. So if you don't have a short RG that you can treat perturbatively, you don't have much power like to see what's gonna happen in this theory. What I can tell you is that the kind of if you want still like these operators still preserve some kind of symmetry, so this will be what you can try to use, but I mean the symmetry in this IR fixed point that is preserved, it should be the one of either this non-SUSY writable, probably this non-SUSY writable operator that's still preserved in Sn-2 instead of On-2. So this you may try to use that, but
this is formal, no? But I mean,
may I make a comment because this is a long story. It goes back to Daniel Fisher. Daniel Fisher has said that exactly this object F4 becomes relevant. It runs to infinity. It leads to complete reorganization of the theory, and that can be treated in some cases for functional RG. It's very difficult for the Ising model.
how do you know it becomes relevant unless you do the calculation? Because this conclusion that phi to the fourth becomes relevant is based on a bare dimension of the field that you're using for this conclusion. But in fact, by the time you got to 4D, the dimensions get renormalized, so maybe this is no longer true, or you have to do a calculation.
Yeah, that's why I can't calculate exactly your critical dimension, but the mechanism is always the same. It's always this.
Well, I mean, maybe this mechanism doesn't take place if the dimensions get renormalized.
No, but you tell me the guy becomes relevant.
Some other guy, not because there is a bunch of guys which collapse around 0 dimension, as you say.
No. You say F4 becomes relevant. And I translate this, the cusp is generated. Just a translation.
So there is a little bit of problem. I don't know. Emilio told me that he has to leave at 5 sharp to get a test.
Yes.
So
okay. I propose Slava will just continue, maybe.
So Emilio, if you have very nice slides.
One very brief question.
You have very nice slides. Maybe you can leave us the slides, and Opera team and myself we will continue the discussion because there are many questions.
Sure. I'll send you the slides.
Yeah, and so that we can thank you before, so that you can enjoy our virtual uploads before you have to rush out.
Is there a reference to everything you said?
Yeah, there is a reference in the beginning of.
Send it.
Yeah, in the first slide there should be a reference. Yes.
Okay.
So, well, thank you very much.
Thank you.
Thank you very much, Emilio. It was very, very clear.
Thanks.
Could I ask maybe a couple of questions? One, a very general question. Does it make sense to have anything like a random field Potts model? Is that a conceivable generalization of all this?
Yes, we wrote papers about that in the 80s. Random field Potts model for general number of states.
Right, but then would there be some kind of supersymmetry connection in that case?
There was dimensionality shift there also.
And the other slightly technical question is, for the calculations in the epsilon expansion, which went to 2 loops, I mean, I guess you cannot map them onto standard RG equations in 6 minus epsilon dimensions because of the funny propagators and so on. Is that the case?
Operative, would you like to answer that?
So by standard RG equations, can you specify what exactly?
Well, I'm thinking in the kind of stuff, for instance, that John Gracie has done to quite high loop orders, starting from some versions of the phi cube type theory with the conventional kinetic term. I mean, his calculations go to high orders, but perhaps are not relevant for this kind of model.
So what I can say is we can certainly map our computations to a computation done by the paper by Brizan and his collaborator. So, and that was also using replica trick, a version of replica trick that preserves the SN invariance. So we could see that, and that is and that is also standard epsilon expansion, and we could see that aspects of our computation is reflected in that calculation, and I'm not sure.
Well, I guess the question is higher loop results somehow contained in the literature, or is it something you have to do from ab initio?
I think it's not contained in the literature because the diagrams are so the diagrams are very different because there are calculations. So whatever diagrams you compute using supersymmetric propagators with supersymmetric fields, those ones can be mapped to the usual phi to the fourth diagrams.
Yeah.
But for these particular operators, non-SUSY writable operators or SUSY null operators, you have to do you cannot do the calculation in the supersymmetric formulation of the theory. You have to do the calculation in terms of these chi fields. And so you are computing some set of diagrams, which is kind of, which is different. So they do not they do not compute the dimension of any phi to the fourth operator. It's just like a different thing. And so it has to be done. It has to be set up from scratch. I mean, apart from the beta function. So the beta function, of course, the beta function is the same as in the phi to the fourth. And the field, the wave function realization is the same as in phi to the fourth. But the factors to make the operator finite, those are different. Those you have to compute from scratch.
Yeah.
Okay.
I think you can calculate them in the supersymmetric theory if you double the set of your fields. Because then they are no longer forbidden. And that's what you would do if you start from the supersymmetric method. But
it's the wrong thing to double the set of the fields.
It's not wrong. You can do this, I mean, unpunished.
No, it's wrong. In fact, I would like to comment. There was some mention here by the work of Tardieu and Tissier. And I wonder actually how many people read those papers, like because I tried to read their papers. I reviewed their papers in some appendix in our work. But when I reviewed the papers, I emailed some, let's call them biggest experts in this field for comments. And I was shocked to discover, that I'm not going to name names, but those people just basically replied that they never read those papers, that I, as a newcomer of the field, already know those papers better than them. So I read those papers, and I can say that those calculations do not start from the first principle Lagrangian. In fact, they do something very weird, which is they don't start from the replicated Lagrangian. Instead, what they start from is that they start from the replicated Lagrangian, they get to the supersymmetric theory, and then they say, oh, but we know that the supersymmetric theory is wrong, so let us replicate the supersymmetric theory once again. So they do the replication of the supersymmetric theory, which was already obtained by replication, and start setting up on top of this the FRG machine, which gets some results after that. But that's wrong, because it's like double counting. You should not, in fact, the Lagrangian that they get, I claim, the Lagrangian which they start from when they apply the FRG machine, I was not able to obtain it from the first principles from the replicated theory. It just contains some terms which they put in by hand, and then they start turning the FRG crank. So I challenge anyone to derive that Lagrangian from the first principles. I was not able to do it. And so I think their scenario, which was reviewed here by saying that the supersymmetric fixed point becomes unstable below a certain DC. That's what Marco Picco said. I think that's not actually what they claim in their papers. The supersymmetric fixed point does not become unstable below DC. It just disappears below DC. So it's very different from what we say. So in our scenario, there is a supersymmetric fixed point that exists for any DC, and it becomes unstable. In their scenario, the supersymmetric fixed point just somehow disappears whatsoever below DC.
And then what?
I mean, it disappears
Nothing,
because there is an RG flow to a different fixed point.
But they should still be able to find it, and they don't find it. I mean, there is no, doesn't exist. It's not like
you can
in our
force
case,
it to exist, but
no, that's not what they say. They just say this, it annihilates. They say that the supersymmetric fixed point annihilates with another fixed point. That's what they say.
okay, there are things they say, and there's things what they do.
No, I mean, if you look at their picture, they really draw a parabola where there are two fixed points which annihilate. So that's a plot in their picture, which is the result of their calculation. It's very different from what we say. We say that there is a fixed point and there is a branching off. So the scenario is very different. So, okay, I'm not claiming that what they did, I don't want to make very strong claim. I'm just saying that I was not able to make sense from what they did on a formal level. And I challenge anyone to explain this to me, how their Lagrangian follows from first principles.
May I switch the discussion into another direction? The claim here was that below DC, there appears a relevant variable that leads us to a new fixed point. But this new variable is now expressed after a Cardi transformation and after a replica transformation, and I lose its connection to the original problem. The original problem only had an Ising model with random fields. Now, of course, when we iterate the original problem, in which we had an Ising model and random fields, we will generate under the renormalization other random variables. For example, the random field will generate a random exchange. It will generate a field that couples, a random field that couples 3 sites on the lattice, and so on. Many random terms will be generated by the renormalization. And then we could replicate and deal with all those correlations. These random variables that will be generated may be correlated between them. There will be a whole distribution of random terms in the renormalized random Hamiltonian. And those new random terms which are generated under the renormalization in the random real space somehow should yield these new supersymmetry breaking terms in the supersymmetric replicated problem. So I would like very much to see a calculation which first iterates the Hamiltonian with the original random fields, generates renormalized random Hamiltonians with new random terms, and iterates that several times and ends up with a very complicated network of random Hamiltonians, and then do whatever is necessary to deal with those random Hamiltonians to see if they contain new terms that break supersymmetry.
It was written down that the operator was phi I minus phi j to the power of 4. I and j being replicas and phi just the physical field.
Okay.
That's also what Daniel Fisher says, that that's a relevant guy. He first said this in 1986.
No, all the operators I'm referring to in my discussion would be highly irrelevant near 6 dimensions. But as I said, we can, if we find them near 6 dimensions, we can follow them at lower dimensions. And at one point, they may become relevant and then represent this new supersymmetry breaking behavior.
Can I try to
we need to identify all these random generated terms, and I am not sure that after all these transformations, we don't push ourselves to some subspace of the Hamiltonians and we miss some of those terms. Whatever we are discussing in 4.7 dimensions should have been there already near 6 dimensions.
Yeah, I can answer.
They may be highly irrelevant, and therefore we ignore them.
Yeah, I can answer. So there are 2 questions here. One question is indeed there are 2 different ways to do RG in these random systems. One way, as you say, we can just try to renormalize Hamiltonian, disorder, everything, and then we don't need replicas. That's kind of.
We don't even need replicas.
We don't need replicas. Yeah, they don't need replicas. So that's like a super. Yeah, that's super rigorous, but it's also extremely hard. So that I don't know how to do this.
I don't think it's extremely hard. We can classify the generated terms by their degree of irrelevance.
I can tell you why it's hard, because fields in this approach, they don't have a well-defined scaling dimension.
No,
the only way we do know how to do RG systematically, I mean, apart from FRG, is when you have fields with well-defined scaling dimension. So that's this approach that you propose. I mean, one could yeah, I agree. It's a valid approach, but I don't know how to do it. And so maybe somebody else knows. I don't know how to do it. So
I know, but I'm too old to start that.
So that's why we did this other way, which is eliminate the disorder, do the replicas, and then so okay, this creates, of course, some questions: is replicas valid, not valid, and so on. So, but then I also want to go back to your previous comment, which you asked Emilio. You said, okay, but back when you did your calculation, which discovered dimensional reduction for the first time, you didn't do the replicas.
No.
You didn't do the replicas, and you saw dimensional reduction. And so how can this be reconciled with our current finding? I can tell you how this can be reconciled. So indeed, you didn't do the replicas, but you also you did something which was not particularly justified. You just said, okay, this set of diagrams looks like it's the most infrared singular diagram, so let's just keep those and drop everyone else. Now, the only way I know how to make rigorous sense of dropping diagrams is setting up RG. Otherwise, it's just a perturbative reasoning. So you did not set up RG in that paper. So in particular,
let me follow up on what you said. You're right. We identified the most important diagrams under infrared or whatever singularities. We could look at the next two leading diagrams in which we ignore some of the dressings by the random fields on the diagrams. There will be a hierarchy of diagrams which are more and more irrelevant as we would do that, but some of those diagrams might become relevant below 4.7 dimensions. We don't know that.
Yeah, they could become relevant, especially
included in the theory, except that we ignore them because
no, they are not included in the theory. They are not included in the theory because you don't include some couplings, which are in principle allowed by the symmetry, but you start from 5 to the 4th Lagrange and you don't include all the couplings. Okay,
but one could follow up in that direction also.
Yeah, one could, but that's indeed very complicated. Again, I don't know how to do this.
To allow
can I ask a question?
Epsilon, one could do that.
Yeah, sorry. Sorry, Miguel also wants to ask a question for a long time.
Yes, sir. So if I understand correctly, so this supersymmetric fixed point, I should think about it as a non-unitary CFT, which includes as a subsector a D-2 version of the Ising model, right?
Yeah, that's one way to say it. Yeah.
And in this enlarged non-unitary theory, at some point, as I vary D, there is one operator which happens to break SUSY, which becomes relevant. So my question is, anyway, since this is a non-unitary extension, so for instance, if you are in D equals 4, where this SUSY theory will be, you'll have a non-unitary extension of the 2D Ising model. I mean, do you have any ideas on what this completion of the 2D Ising model should be?
No, because you have to set up a bootstrap problem. In fact, so there was a paper, so people ask usually because people see that there was a paper by Hikami on bootstrapping on bootstrapping random field Ising model, and I think it was a nice idea to try to bootstrap it, but in that paper, and one could try to do something like he tried to do, but one should be a bit more systematic, and one should indeed, if one wants to bootstrap the supersymmetric fixed point of the Ising model, one should put in supersymmetry from the start by hand, and then which he did not do, and then one could, so one would say, okay, here's my theory. It has a subsector which is the Ising, and now I have to extend it to a bigger theory, which is now we're going to have this supersymmetry. And consistently with supersymmetry, I have to find an extension. And if I manage to do this, then I will be able to measure the dimension of these extra operators that we are talking about.
Yes.
And see if they do become relevant or if they don't become relevant.
Right.
So that's a valid problem, but okay, Hikami didn't really do this. So he did something much more simple-minded, and I think
Hikami was here until an hour ago.
Yeah, well,
asked him.
yeah, well, I studied his work, and it's also reviewed in our paper, so you can take a look. So I think somebody should try to do it again using this using this new understanding of supersymmetry.
So we know that there are these non-unitary or logarithmic extensions of 2D Ising. We've heard about several of them during the conference. Like we have a when and then you send n to 1, or you have pots and you send q to 2, and this way you enlarge the theory. But this is yet another non-unitary extension.
Well, this is yet another extension because it lives in 2 dimensions higher. So all these other extensions that we consider, they live in the same number of dimensions. Well, this one lives in 2 dimensions higher.
All right, and the dimensional reduction only holds for this subsector.
So when you try to perform the dimensional reduction by setting operators in a subspace of this D plus 2 dimensional space, then certain representations which exist in this supersymmetric theory, which are classified, I mean, these are representations of this OSP D/2 supergroup, and they are classified by Young tableau and so on. When you go to D dimensions from D plus 2, then certain Young tableau, they are no longer allowed by SOD symmetry. And so representations with those Young tableau, they just project to 0. So if you just look at the D-dimensional Ising model, then you don't know anything about those representations to begin with, which are supersymmetric still. But on top of this supersymmetric sector, we have to still add this extra sector, which is the SUSY breaking operators that become relevant. So it's a much bigger bootstrap problem, and I don't know. Yeah, it has not been done. Complicated, looks complicated.
Okay, Miguel, you have a lifted hand.
With the random field Heisenberg model.
I have a lifted hand.
Yeah, there's a lot of work, Anna. We have to start somewhere. Yeah, there's a lot of literature. In fact, some people, I mean, like professionals who work on these random field models, they usually indeed try to say something about not just Ising, but also about Heisenberg, and or maybe try to do everything together.
Is there any issue of supersymmetry there?
If there is an issue of supersymmetry there, yeah, to my shame, I don't remember, but maybe Kai can say. I think it's also broken there. I don't know. Kai, do you remember?
Can you remind the question?
So the question was, if you now consider higher, like Heisenberg, random field Heisenberg model, if there is any interesting question related to Parisi-Sorlas supersymmetry in that context.
And what exists is a 2 plus epsilon expansion. So, sorry, 4 plus epsilon. So it's a nonlinear sigma model version for a random field problem. And this is perturbatively controlled around 4 dimensions. It's in the work. Feldman did something.
So in that case, the upper critical dimension is 4, not 6. What's the?
No, it's a lower critical dimension.
Lower critical dimension.
The random field Heisenberg model has the dimensionality shift from 6 to 4. But at 4, it loses long-range order, just as the usual XY model loses it in 2 dimensions. or Heisenberg model. So the question is, does anything peculiar happen between 6 and 4 dimensions for the random field Heisenberg model as compared to the random field Ising model?
Well, I know that FRG people, they did those calculations, so but I don't remember what the conclusions were, and yeah, and you see that I also not sure what was the starting point of those calculations.
So, for instance, for n equals 3, 4, there is a fixed point above 4 dimensions, and when you reach n equals 2.83, this fixed point plunges below 4 dimensions. So I mean the nonlinear sigma model can't handle Ising, but I mean morally you expect it's consistent with the Ising fixed point being the Ising fixed point in 3 dimensions. There is still a transition in 3 dimensions for random field, so it's consistent with epsilon expansion, 4 plus epsilon expansion. So 2 is already special.
So are there any more questions? Or Kai, did you finish?
Yeah, I finished.
So is the question, or I just wanted to say that the smoke and gun of our scenario, if somebody manages to tune something in the random field Ising, say in 4D, disorder distribution or something else, and manage to find a SUSY fixed point in 4D, which is supposed to be unstable, but it should exist.
I have a question for you.
Yeah.
So
but I mean, this you can do with a long-range Ising model now, and you can tune.
But I mean, you can always do it. But so we claim that in the random field Ising model, forget about long-range model. We claim that in the random field Ising model in 4D, there exists a SUSY fixed point. It's just difficult to find. It's not reachable, but if you tune things, you should be able to find it. It's a multi-critical point.
But you have to tune the disorder.
You have to tune something, disorder.
The disorder which you have in an experiment will not like this and will still grow.
Sorry?
The disorder in the real experiment will not like to be tuned.
No, but I'm not talking about the real experiment. I'm just saying that if you want to distinguish our scenario from Tarjus, there's a very simple way. Tarjus says no supersymmetric fixed point in 4D. It's annihilated. It disappeared, period. We say it exists in 4D. You just have to tune things. It's a different scenario, and it could be in principle distinguished by some careful Monte Carlo simulations tuning disorder.
Yeah. I don't agree with you that the distribution is not variable experimentally. The experimental situation is that you have random fields in an antiferromagnet with uniform field. But then the random field has just 2 values, plus or minus h, and with h being the external field. And that is not a distribution like the Gaussian or the Poisson distributions that were described before. This is a distribution with 2 peaks at non-zero values of h, and that leads to different results. So I would indeed like to see more research into that kind of distributions. At the mean field level, I know that they give first order transitions and then tri-critical points into second order transitions. But that may be a good direction for the Monte Carlo people to vary the distribution and go between those 2 distributions. For example, a flat distribution near zero might give different results than a peaked distribution, and so on.
In the field theory, you would need to look at higher cumulants, and this is awfully complicated, and nobody has done that. At least not in this rather complicated model.
Right. The higher
So I always
cumulants
suppose it's
might be
Gaussian
the
disorder.
we are looking for.
At the level of correlation functions, is there a difference between your scenario? I mean, can you say if there is a difference between your scenario and the scenario of having avalanches that give you the cusp in the renormalized disorder correlation function?
Well, I don't know, because you see, we only did the calculation, we only did the stability calculation. We did not compute.
That's what
we did
Emilio
not
was
compute.
telling me.
We did not compute. I mean, we can compute.
I mean, can you at least envisage a way?
Yeah.
Of say computing, the kind of violation of the kind of violation of a supersymmetric word identity, mainly fluctuation.
Yeah, it's definitely possible. I can give you an example. So what we could do, and even not so, it wouldn't be so difficult to do. So this operator which becomes relevant. Okay, once it becomes relevant, suppose it's strictly relevant, it triggers some RG flow. So we could get, maybe for d equal 4, this operator is still weakly relevant. So we could get from the SUSY fixed point to the non-SUSY fixed point just by doing conformal perturbation theory, which would be a very different way to get a non-SUSY fixed point.
But what will you use as a perturbation?
This operator which became relevant.
Yeah, but you don't know what it is.
Well, we have a guess, but suppose that we work harder, we set up Bootstrap, or we set up.
Then you should follow it perturbatively, and maybe it will take you to another fixed point.
Yes, yeah, but okay, this is ambitious, but maybe one day we could learn more about this operator which becomes relevant, and we could follow it, and then just like you Amnon explained to us that by following the cubic breaking operator, we can get from Heisenberg to cubic. Also here we can get from one fixed point to the other, and we can, for example, predict how this critical exponents eta and eta bar, how they're going to change.
So maybe I suggest a better scenario. You start at 5 dimensions. And find that irrelevant variable at 5, and then you continuously change the dimension from 5 downwards to 4.7, and then maybe it will start becoming relevant, and you will see it in your calculations.
Yeah, something like that. So these things could be done. But Sylvia asked me, what actually can we compute in 4D?
No, I ask what you can compute in your DC 4.7 minus epsilon.
Exactly.
Well, in 4.7 minus epsilon,
yes.
we could estimate how eta and eta bar, for example, start changing.
Okay,
no, but you have to find the
besides eta and eta bar, what I really would like to know is what correction you get to the response, because I mean, let me insist that one of the word identities just tells you that the response function is related to the curvature of the minimum in which you are sitting.
Yeah.
Okay? Which is the usual response function if you just have one minimum.
Well, it's usual for me, but I don't have this intuition so well developed. But it's my understanding that when you talk about response, are you talking about some small deviations from equilibrium, or am I wrong?
No. What I'm saying is that if the effect is an effect of having many minima, and then when you change slightly the field, you jump from one minimum to another. Okay, this gives you a contribution to the response function. And the idea of functional renormalization group, basically, the idea of Fisher that Kai was mentioning, is that this gives a singularity, and this gives you, this gives you a singularity that breaks the supersymmetry and breaks the dimensional reduction.
What is the observable? What is the response function observable in our language?
The response function.
Yeah.
The connected correlation function.
Ah, okay. That was some part of
well, because
terminology that I was missing.
You get it taking the derivative of magnetization with respect to external field.
Okay. That I was missing this terminology. Okay,
sorry,
so we should consider then you are saying that we should think more about connected correlation function, and what should we compute about it?
So
how it changes.
So the connected correlation function, I'm calling connected correlation function, but it is the connected correlation function. It's just using the fluctuation dissipation theorem, basically. Okay, so you compute the derivative of the magnetization with respect to an external field. Okay.
Yeah.
So this is it's a definition of susceptibility.
Yeah.
Okay. Now, if you are in a minimum or if you are in equilibrium, you get the fluctuation dissipation theorem that tells you that basically this response function is related to the curvature of the minimum in which you are sitting, the Hessian, okay, the Hessian matrix. Okay, so this is just the inverse of the Hessian, and this is one of the word identities. You can see that this emerges. So this is elementary thing, but it emerges as one of the word identities of BRST symmetry. So you don't
what emerges as BRST symmetry relates you one observable to the other. Which observables are now relating?
So it relates the response function to the curvature of the minimum, to the inverse of a Laplacian plus V double prime, okay, of phi.
It relates one observable which makes sense in field theory to another which doesn't make sense in field theory. It's just some observable that makes sense physically, but does it have an independent definition in field theory? Because in field theory, you say word identity. Word identities in field theory, at least, are very, very.
Yeah, if you like to say that it relates the correlation function I phi hat or omega, as you call it, omega phi to psi bar psi. Okay, so it is this word identity.
Okay.
Now, these are. I was mentioning the physical meaning because the physical meaning, after all, we are talking about physics, no? But it is that word identity. That word identity is important because it is fluctuation dissipation theorem, from my point of view. And this is broken, the breaking of that identity, you can understand, because you say, okay, if I have a single minimum, I understand this identity in the terms I was using, in the terms of minimum, the fact that if you pull the system, the system just displays it inside that minimum. But then, if you have that, if you introduce a perturbation, sometimes the system jumps away, because you change minimum you change the minimum configuration. You have an avalanche, then you have some additional contribution, and then the word identity shouldn't be valid anymore. Okay, so well, it is.
In our theory, word identity is not going to be valid because the moment
I understand. So,
but
because you are breaking.
But we won't have this picture. We won't have this picture that you're describing. It's yeah. We never use this picture, so it's hard for me to connect. I mean, I realize that you have this great intuition.
No, it's not the great intuition.
But we don't have this intuition, and we never used it. We just used field theory and RG. So I don't know what to say. Yeah, so we are able to make a calculation. I mean, we hope to be able to make calculation one day.
I mean,
but you're saying you're not going to be satisfied.
You criticize the rules, and actually, I must say that I'm not convinced on this double replication. I mean, once you have the supersymmetric, you don't need to replicate, or when you replicate, you don't need to introduce fermions and then to replicate again. I mean, on that I agree perfectly with you. On the other hand, Tissier and Tarjous have this physical picture of avalanches, which are the ones that cause the supersymmetry breaking, which is important, which is also the one, by the way, which is also the one that Chi has. Now, if you look at the problems of Chi, which are essentially manifolds in random media, okay, which are simpler problems than the random fields. Also there, if you look at the level of perturbation theory, you would get dimensional. I mean, naive perturbation theory, you would get dimensional reduction. But then there, the problem is understood much better, and there perturbatively in 4 minus epsilon. You find that the functional renormalization group gives you the singularity, the cusp singularity, which is caused by avalanches, that allows you to escape from dimensional reduction. So I think that, for example, one nice thing to do to test your method could be to study random manifolds.
But we did study random manifolds. We have an appendix about that, and yeah, because I read.
I'm sorry, but I mean your paper is 80 pages.
Very long. I mean, I communicated with Kai a lot, and I studied his work. And okay, I don't claim that I understood all of it, but I made an effort. And then what we managed to reproduce one particular aspect of his story in our language. Of course, not the full story, which is very beautiful and complicated, but the loss of supersymmetry. So there's one thing on which we disagree with his interpretation. I'm sorry, I think he left, so maybe he's not going to be able to answer. But so he says in his papers that the loss of supersymmetry cannot be understood in perturbation theory. So we disagree. If we just do exactly what we do for the random field Ising model and apply it to his Lagrangian, so we discover that there is a SUSY null operator which becomes relevant precisely where supersymmetry is lost. So, of course, if you do a transformation to the SUSY fields right away, then the SUSY null operator, you will forget about it and you will not see it, and then you say, oh, well, there is supersymmetry. No, but you have to be careful. You shouldn't do transformation to the SUSY variables before you check that all operators are irrelevant. But in fact, there is one SUSY null operator which becomes relevant when he discovers that the SUSY fixed point becomes unstable. So on this point, sorry?
What is that operator?
It's chi squared. It's the operator. I mean, he has a much simpler global SUSY. It's a more simple story, but okay, the question of stability of the SUSY fixed point, our formalism gives exactly the same answer as his formalism. Of course, he then can do more, because he says, okay, the SUSY fixed point is unstable. Now let me try to find a true fixed point, and here he starts doing FRG and he extracts some exponents. This we don't know how to do.
You can do it perturbatively.
We could do perturbatively. Yeah, we could do perturbation. But anyway, we have not done it yet and so on. But as far as stability of the fixed point, of the SUSY fixed point is concerned, there is no contradiction at all between what he does and what we do. Even though we don't talk about avalanches, and so somehow we get the correct result.
So really the question is whether the supersymmetric fixed point disappears or not. But how it could disappear? Because I mean, this is a symmetry.
No,
excuse me.
It cannot disappear. I mean, it exists rigorously as a field theory. It rigorously exists. I mean, it cannot disappear.
Could somebody tell me who's the host of this meeting? I'm only co-host. I started the recording, but I had to leave.
I am host.
You're a host. Can you make Slava co-host or something that I can disconnect?
I make Slava off.
Maybe we should stop.
Or maybe we should stop. I don't know.
I don't want to force you to stop. I just tell you.
I mean, I'll stop when people say that they have no questions, but I'm enjoying discussions with Silvia.
I have a question.
It's very interesting, but it's getting late.
But Amnon, I'm sorry. You have +1, right, in respect to us. So if you
quick question: What is an avalanche?
So
I've never heard avalanche in this field.
So sorry, one moment.
Long story, but
Silvio, also because I have to go. Slava, you are the master of the situation.
Yeah.
So you can, I think that you can finish the session and also the recording, or we can stop the recording now.
Well, I mean, there's some pedagogical introduction to avalanches, so maybe.
No, this is going to be recorded. Yes. So sorry. Go.
The cutoff on the whole thing is 6, because at 6 I also have to leave. So there's no, the discussion is not going to be indefinite.
Okay. So the question is, what is an avalanche? So the short answer is this: in disordered systems, in general, you have complex Hamiltonians which have many local minima. Okay. And then when you add with a perturbation, and in general you are interested, say, in the global minimum. Then when you add with the perturbation, okay, you can have level crossing. Okay, so you have that levels depend, each one depend on the perturbation in a different way, and at some point you can have level crossing. When you have level crossing, you can have that you may want to jump, because I mean you need to go into the new ground state. You need to jump to a configuration which is very different, because it is a different minimum, which is not just a smooth deformation. That is what you have when you follow a minimum, but when you have to go to a completely different minimum, you can have a macroscopic rearrangement of your field, basically. So this is what it is, an avalanche.
I would just call that a first order phase transition. Is that wrong?
No, it's not a first order phase transition, because I mean the rearrangement can be large, but I mean it cannot. I mean, first order phase transition is when you pass from water to ice. It's not of that kind. I mean, the minimum in which you fall is different from, but it has the same. It can have the same statistical properties, for example.
Okay.
Okay. But yeah.
But is there any, so these avalanches, they presumably exist whether the fixed point is supersymmetric or non-supersymmetric? They always exist.
Absolutely.
But is there some?
But then, okay, then Tarjous and Tissier, they have a criterion I mean, they have to say, okay, then the avalanches have a certain so avalanches typically occupy a certain portion of space. They have a typical spatial extension, and they have and they may have a fractal dimension, a typical fractal dimension. Okay, they are characterized by a fractal dimension. And this is something that you can measure, and in some systems, the fractal dimension of avalanches has been measured. And then I mean, you have to evaluate if okay, the avalanche contribution to the response function always exists. You have to evaluate if it is the dominant contribution or it is not the dominant contribution. You may have that the regular contribution, which is the one that you get just following a minimum, because I mean, you know, the typical thing is that you follow the minimum, and then sometimes you have some critical values of the field, so to say, that makes you jump from one minimum to the other. So it depends. I mean, certainly you have those values of the field, but then it depends if you are dominated by the regular behavior or by the avalanches. Mm-hmm. And then they have a criterion that depends on space dimension, on the dimension, on the fractal dimension of avalanches, that tells you if avalanches are relevant or they are not relevant. And
but what is the claim? That for SUSY fixed point, avalanches are subdominant? But
they are subdominant, absolutely. I mean, they have the claim, for example, what they find. So they have some inequality between exponents that they have rules that. And what they find is that in 6th dimension, there is room, you know, to go. I mean, this difference between space dimension, fractal dimension of the avalanches plus 4. I mean, I don't remember the exact formula. I mean, I probably have written in my notes. No, but I mean, I don't want. I cannot share the screen now. So there is this inequality. In 6th dimension, for the random field design model, estimate the fractal dimension of the avalanches as 4, which is an estimate. I mean, I don't know how. I mean, what is the validity of this estimate? But I have this estimate. If you accept that estimate, you find that there is a strict inequality that it tells you that you are supersymmetric in 6th dimension. And if you go, and there is room for supersymmetry below 6th dimension. On the other hand, if you do it for random manifolds, okay, the relation is verified as an equality in 4 dimensions. That means that there is no room below 4 dimensions for a stable supersymmetric fixed point. Okay, so this is the reasoning that they do. Of course, there are a lot of assumptions that you have to accept. Some of them I don't understand. But
I mean, they talk. I noticed that they talk a lot about avalanches, but yeah, I always had the impression that it was kind of a nice story, like it was a nice juicy story, but that's not how they actually do the calculations. Because they make this nice juicy story. Oh well, there are avalanches, but then they're like, no, but it's for the introduction.
No, but if you get, because I mean okay, in the language of the functional renormalization group, you have this renormalized disorder correlation function. Now basically what you can do, you can this renormalized correlation function is what is basically, suppose that you take to slightly different fields. So two systems with slightly different fields. Okay.
Mm-hmm.
So those are, and then you want to know what are the correlations between when I say fields, slightly different fields, I say external fields.
Mm-hmm.
And then you want to know what are the correlations between the magnetization field configuration in one of the system and in the second of the system.
Mm-hmm.
Now, the generating function of those correlations, say, for example, is the second move, so is the correlation function of free energy of the first system, the Landau free energy, the first system with a given field and the second system with the other field. Okay. So I don't know if this is clear. So you have on the one hand, what you consider, for example, in the replica method, typically is the average free energy for a given realization of the field. But you can also look, say, okay, now I take two systems with the same realization of the field, but different external field. And I look at the correlation function of the free energy.
Yeah, I can do
energy.
this. I can do this. Yeah.
Yeah. Okay. Now the claim is that if you have avalanches, this object is singular, and in fact the renormalized correlation function of the disorder, which is the second derivative of this object with respect to the external field, has a cusp. Okay, if delta H is the difference in field in those two systems, okay, you get that the second derivative is proportional to modulus of delta H. Okay, and that you can I mean that is physical in the sense that if you evaluate phenomenologically the contribution of avalanches, so basically what you have to say is that when you change your external field by an amount delta H, you have a probability that the probability of having an avalanche in this interval, delta H is small, you have the probability of having an avalanche in this interval is proportional to delta H. Okay, if you accept that, then what you get is a cusp in the renormalized disorder correlation function. Okay, so this is the whole story of Danny Fisher, as Kai was mentioning, and of Kai and Pierre Ledoux-Salle that have been doing an industry of that.
Silvio, okay, since we only have 5 minutes left, I wanted to kind of summarize. So it seems to me, so you understand, we are not experts like we are newcomers to this field.
I also I'm a newcomer. I mean,
so okay, so there was one thing that we tried to internalize in this business, which is the class of observables which are just correlation which can be described as correlation functions within this replicated theory. Now you seem to be telling us that there is this other class of observables related to avalanches and cuspiness that we have not been paying attention to, so we should start paying attention to those observables. So I do not know at present how to describe these observables in field theory. So can we describe them in our field theory, or should we extend the field theory somehow?
Let me tell you, because you see, when you consider those correlation functions that I was mentioning between free energies at different values of the external field, basically you need to replicate a pair of systems, one with a given external field and the second one with another field. So what you get is a theory, is a replicated theory with 2n replicas, if you want, or say n1 plus n2 replicas.
No problem, we can do this.
No problem. Where you have an invariance, which is Sn1 cross Sn2.
Okay, but alternatively, we can just take our theory and then just add some terms, which break Sn to Sn1.
Absolutely.
We can do this. In fact, we did some exercises like that because
Absolutely.
we have an appendix in our paper where we tried to do exactly what you are describing, trying to see if we will ever get Tavjus and TCA theory, and we never got it. But okay, now we're talking about different things. So just let's do this two systems, and then we can do what?
And then, as I say, I mean, and then you have to compute that and see if that object. I mean, you must be able to compute that object, no? Because I mean, if that object, I mean, if there is a singularity of the kind that they are talking about, this famous cusp singularity that emerges in the analysis. I mean, that I don't know. I mean, as I say, what Kai does is this functional renormalization group with replicas where.
Well, Silvio, I think we have to stop because I was promising to talk to someone at 6.
Okay,
but
no, I mean,
okay. Hopefully, it's only the first time that we are.
Hopefully, I mean, it was very interesting, very interesting.
Yeah, so I find your way of explaining things very approachable. So hopefully, we will learn more from you in the future.
Yeah, I also hope to learn from you.
Thanks for having the idea for these discussions. It was a great idea.
Okay, thank you very much.
Okay,
Bye-bye.
see everyone. I'm stopping the recording.